Greetings. Let's remind ourselves of the steps for solving exponential equations using logarithms. The essential thing we have to remember is this relationship between a logarithmic expression and an exponential expression. I have two different ways that I've indicated that here on the right-hand side. First, with the notation, the idea that base raised to the exponent gives us some number n is the same as saying log with that base of the number n equals the exponent. Remember, logarithms are exponents. The second way I could think about that is sort of symbolically where things go to fill in boxes. That's what I've done here. So the key thing is to remember the base is the base, meaning when you have that base of your exponential expression, that becomes the little subscript on your logarithm, but the role of the exponent changes to being an output when we move from exponential version to logarithmic version. And as a reminder, these are the exponential form, and on the right we have the logarithmic form. So my steps for solving an expression, an equation involving logarithms, really can be thought of in two phases. First, I need to get something in an exponential form so that I can switch it to logarithmic form. And then once I've switched it, I have to do work inside the exponent to solve for my variable. So with our first example, we'll do one with base 10. So if I want to solve this equation, I need to think first of all about identifying where is my exponential term, my exponential part. So I want to identify the sort of b raised to the n part, and then I need to isolate it. So what I mean by isolating it is that I want to make it so it's by itself on one side of the equation. So let's go ahead and find that b to the p part, that solely exponential part on the left. So what I notice looking here is that I have a base of 10, and I'm being raised to this x minus 4 power. That's my b to the p part. Those two circled pieces, that base with that exponent on it, that's the only thing I want on my left-hand side. So to do my isolation in this case, I have to get rid of anything else that's on that side. And here I see I have a 3. So I'm going to use that inverse operation, the thing that undoes 3 times something, because that little dot means multiplication. So let's divide both sides of this equation by 3. So I'm going to divide by 3 on the left and on the right. Dividing the left-hand side of the equation by 3 eliminates it. So that portion is missing. What's left then is this portion I'm circling here. And I'm going to copy that. So now I have 10 raised to the x minus 4 on the left. On the right-hand side, I've computed 42 divided by 3. 42 divided by 3 is 14. So now I'm at my next step. I have something where my unknown is in the exponent. So the next thing I'm going to do is, I often just call it logging it, or we're going to convert from exponential form to logarithmic. So if we want to think about the color coding we've been using, there's one thing left to color code, I suppose, and that's that output. So when I write my equivalent version, I'm going to write log. I want to keep the base as 10, because that's my base, of, well, that's where the output has to be, and then it's equal to my exponent. So the exponent is now one side of my equation, and that means I can get at the variable. Remember, this expression logs base 10 of 14 is a number. It's a number that I can compute, especially in this case, since log base 10 is a button on my calculator, the log button. So last but not least, the third step is now to isolate the variable, or solve for the variable, using our basic algebraic inverse operations. And I just have to treat that log expression like it's a single number. So in this case, I'm going to take the log base 10 of 14, whatever number that is, and if I add 4 to both sides of my equation, and so with that work, I've been able to find out what x is. Now, maybe this doesn't look like a very pretty answer, but that would be what we'd call an exact answer. I can go further and approximate its value using a calculator. To calculate a log base 10, I just press the LOG button. That's already a log base 10. So I'm going to do LOG of 14, and then I'm going to add 4. And I want to keep a lot of decimal places here. So log of 14 is 1.14613, and then I'm adding 4 to that. And so I get 5.14613. And now I can go at the end of the day and check that that will satisfy my original equation. See if I get out 42. So the check is, does 3 times 10 raised to the 5.14613 minus 4, what does that equal? And I'm getting 42 with, like, in this case, 000 and then 18 or 19. So I got pretty close. We can see that that rounding really did make a difference. That's definitely close enough for the work we're doing here.